Okay, so we got in our number 4 we have a function f of x equals kx squared minus x cubed. K is a positive constant, it says, and let R be the region in the first quadrant bounded by the graph of f and the x-axis. All right. So bottom line here is if we were to find the zeros of this, so we can get an idea of what the picture is going to look like. Our zeros here, if we factored out an x squared, we'd have k minus x. So our zeros would be 0 and k. So we go through 0 and k. We know that this is a cubic function that is got a negative leading coefficient. So that means it should come down, do something like this, essentially. We know 0 occurs twice, so it should hit the x-axis and go back up. So we essentially have that picture. And again, we're looking for the area that's bounded by the curve in the x-axis. So we're essentially going here from 0 to k. Alright, so the part A here says find all the values of the constant k for which the region R equals 2. Alright, so if we want that region to equal 2, we know that that area of the region is from 0 to k of our kx squared minus x cubed dx, and we ultimately want that to equal 2. Alright, so if we anti-differentiate here, we're going to get kx cubed over 3 minus x to the 4th over 4. And if we plug in our k value, we're going to get k to the 4th over 3 minus k to the 4th over 4. Zeros in there are going to make zeros. So if we get our common denominator, we're going to have 4k to the 4th over 12 minus 3k over 4th of 12. So it'll just be k to the 4th over 12 all together when we subtract those two. And again, we want to know when that equals 2. So if we solve that and multiply by 12, we get k to the 4th over or equals 24. So k would be square root of, or square root of 4th root of 24. And 24, remember, perfect 4s would be 1, and then 3 to the 4th would be, or 2 to the 4th would be 16, and 3 to the 4th is too big, so it doesn't have any reduction possibilities, so I guess that would do it. So, alright, so again, ultimately the key issue here is just making sure that we can write an integral to represent the area under that curve, and to then equate it to 2, solve that equation for k. Alright, 1 point for having the integral. You wrote the integral correctly. 1 point for getting the antiderivative right. 1 point for the value of the integral, which is this k to the 4th over 12. And then 1 point for solving for k. 4 total there. Questions on that one? Okay, let's check out part B then. Part B, it says for k greater than 0, write but do not evaluate an integral expression in terms of k for the volume of the solid generated when we rotate this R around the x-axis. So if we go around the x-axis here, we can do a vertical slice and we'd have disks. So that means we go from 0 to k again of our disk method, pi times the radius of the disk, which would be the function kx squared minus x cubed, all squared dx. I would do it. So 1 point for having the 0 to k and the pi, and 1 point for the integrand. Alright. And the next part is the reason why this is a BC problem. They ask us for curve length. It would not be on the AB test. So for k greater than 0, right, but do not evaluate an expression for the in terms of k involving one or more integrals. That gives the perimeter of R. So we had a perimeter problem like this on one of our other ones fairly recently. We know the perimeter from here to here is simply k. That distance from there to there, 0 to here would be k. And then we're going to add the integral here, which represents the arc length. So 0 to k, square root of 1 plus, and that's the derivative squared. The derivative here would be 2k x minus 3x squared, all squared. squared dx. And so don't evaluate, so I would do it. We get 1 point for having at least the right structure here for this part. So if you had an integral from 0 to k of the square root and you had 1 plus something squared, that right structure was worth a point. If you have that part right there, right, the derivative in the right spot, you got another point. And then ultimately having the plus k over here, you got another point. So if you had the whole answer correct, you got the last point. Questions on that one? All right, well, let's check out number 5 then next. We got all right, and number 5 we have a piecewise function given. We know that g of 2 is 5. So we have an initial condition for g. We have a graph of the derivative of g that's made up of line segments. And we're going from -3 to 7, including those two. And in part A it says find the x-coordinate of all the points of inflection of the graph of g on -3 to 7. Notice it's not including those. So in part A we're looking for, again, inflection points of g are going to be where the second derivative equals 0 or doesn't exist. Okay, we can see in this picture that there is nowhere that the second derivative equals 0 because there's no maximums or minimums in terms of where the derivative would equal 0. However, there are corners for this. That means there's spots where the derivative of this picture doesn't exist. And those corners are going to be at -1 and at 1 and at 4. Okay? So the question is which of those three, if any, or all, okay, represent inflection points. Okay? Well, if we look at our picture here, this would be a spot where the derivative of this picture doesn't exist, which makes the second derivative of g not exist. Okay? But the question is, it goes from positive slope to positive slope. So do we change signs here for the second derivative at that point? No. What about at 1, 1? At 1, 1, we're a positive derivative and then negative derivative, so we do change signs for the derivative of this, which is the second derivative of g. So 1 would be an inflection point. Same with 4, we're going from negative slope to positive slope, so we would change signs at 4 also. So that means our two answers here are at x equals 1 and x equals 4. Okay? And again, the question says justify your answer. What could we say for that? Okay? That we could say that g prime changes from what? Changes from increasing to decreasing at this one actually. And then at this one, g prime changes from decreasing to increasing. Which ultimately makes the second derivative of g change from positive to negative. If g prime is increasing, then the second derivative is positive. If g prime is decreasing, the second derivative is negative. Okay. 2 points, one for getting the right values and one for justifying it correctly. All right. Part B here says find the absolute maximum value of g on the interval -3 to 7. Okay. So where do we have an absolute maximum on g of g on 3 to 7, -3 to 7? Well, keep in mind that that g of 2 here we know is 5. Okay. So that's one thing that we do know, right? Okay. So we know that g of 2 is 5. All right, and ultimately, again, this g function can be defined as such. Okay? If we write g of t, it would be from 2 to t of our g prime function dt, g prime of x, I should say, dx. Yeah. Start over. Okay. And then we have a plus 5 out there. Remember, we want this to satisfy the point 2, 5. So again, we don't know a formula here for g. We could essentially write separate formulas, but really not necessary. So if this is the way our g function is defined, right, and we're going on a closed interval here, that we know that g of negative 3 is a candidate for a maximum or minimum. Okay? The endpoints, g of 3 and g of 7. Okay? And we also know where the derivative, which is this picture, where the derivative equals 0. So g of negative 1 is an option, and then g of 2 is an option. Okay? So all those being candidates, let's see if we can figure out what our values are first of g of negative 3. So in that picture, what's that? Oh, shoot, you're right. There's another one. G of 6, right? Yeah, 6, sorry. So 5 candidates, actually. So let's see if we can come up with values of g here. Okay. And actually, we may not have to check all these, but ultimately, we check the 2 endpoints. Remember, on our picture here, if we start at 2, and we go from 2 to negative 3, we're going this way to the left. That means we're going to have a 1, 2, 3 by 1 triangle. So ultimately, again, I know my g of 2 is 5 here at this point. Okay, my g of 3 is going to be 5, and then we're subtracting this triangle because we're going left. So we're subtracting 1.5 times 1 times 3, which would be 3 halves. Alright, and then we're going to be adding this other triangle over here, which is it's a 4 by 2. So it's a 4 by 2, which means that's 8 times a half would be 4. Now keep in mind though that we're going left and it's negative, so actually this gets counted as what? This gets counted as positive, so we're going to go minus 3 halves and then plus 4, and ultimately that would be 9 minus 1.5 would be 7.5. So at this point, that's the clubhouse leader, isn't it? Okay. All right, what about at negative 1 here? Negative 1, the derivative goes from negative to positive. Is that going to be a candidate for a maximum? Oh, so we don't even need to even look at that one. Whoops, I crossed out the wrong one. That one I meant. So we'll keep g of 7 in the mix for the time being. What about g of 6? G of 6 that goes from negative to positive also. So g of negative 6, that one is what? That one's a no. G of 2 is a candidate, but we already know the value for that, it's 5. And then again, our only other candidate then would be g of 7. So, what do we accumulate here on this part? We're going from 2 to 6, that's 4, 4 by 2. That would be another 4, but we're going right this time, and it's below, so it would be negative. So that g of 7 would be 5 minus 4, and then plus, we got a 1 by 1, would be plus a half. So the value there would just be 1.5. So bottom line, which candidate is the biggest? The value is 7.5, which occurs at g of negative 3. So the question was find the absolute maximum value. So the maximum value would be 7.5. Okay. And I guess that's it. We really don't need to tell where. It just says find the maximum value. So our justification is right here. It's the candidate test. Okay. Questions? Alright, so 3 points altogether. We got essentially 2 points for showing all the candidates. Okay. And then your justification and your answer is another point. And again, the actual work here, the candidate work here is the justification. Okay. Let's check out the next part here, part C. Says the average rate of change of g. Okay. So the average rate of change of g, and we know that in general the average rate of change is going to be the slope connecting the endpoints. So ultimately, if we knew g of negative 3 and we knew g of 7, okay, we could find the 2 points in question. We already said g of 3 is 7.5, we said, and g of 7 is 1.5. True? So the average rate of change, again, is just the change from one point on g to the other point on g. So if we did 1.5 minus 7.5, and then 7 minus negative 3, we get negative 6 over 10, be negative 3/5. 1 point for recognizing that you needed to set up the slope. 1 point for getting negative 3/5, correct? What's that? Remember, we're not doing it for G prime here, we're doing it for G. Right. So if we did it for G prime, yeah, it would definitely be a positive slope because we have we can see that the left endpoint is lower than the right endpoint, right? Okay. But yeah, be careful that we're dealing with G, not G prime here. Alright. And then in part D, finally, we have, says find the average rate of change of G prime on the interval -3 to 7. So the average rate of change of G prime, now we need the G prime values, which make our -3, -4 would be at the left endpoint, and then 7, 1 at the right endpoint. So it would be 1 minus -4, and 7 minus -3. Would ultimately give us 5 on top, 10 on the bottom would be a half. Okay, and then the other part here, and again, that right there is just worth 1 point. This bottom question's only worth 2 total. So 1 point for finding the average rate of change. And then the other part, does the mean value theorem apply on -3 to 7? Applied on that interval guarantee that there's a C between -3 and 7 such that the second derivative is equal to the average rate of change. And why or why not? Okay. Does the mean value theorem apply in this problem, in other words? The answer is what? No. Okay. And that's because G prime is what? It's not differentiable. -3 to 7. So 1 point for recognizing that, and there's your 9. Alright, questions on that one? Alright, let's check out the last one here then. We have a BC problem here, so we can see it's got Taylor series involved with it. So we got 2x over 1 plus x squared. And so that being our function, says write the first 4 non-zero terms and the general term of the Taylor series for f about x equals 0. So ultimately, we know that that's going to come from f of 0, which f of 0 in this case is going to be 0. Alright, and our f prime at 0 is going to be our next one. And if we want to find f prime here, we can find f prime by finding the derivative. So we have to go 1 plus x squared times 2 minus 2x times 2x all over 1 plus x squared all squared. And if we simplify, we're going to get 2 plus 2x squared minus 4x squared. It'll be 2 minus 2x squared on top. Alright, and ultimately we can put 0 in there and we get 2 on top and 1 on the bottom. So the next one would be 2. 2x would be the next term. And we're looking for the first 4 terms, it says, right? Okay. So ultimately we need to keep going here, so I'm going to change papers here for the other part. So if we need the second derivative, we would have 1 plus x squared all squared bottom times the derivative at the top, which would be -4x minus the top, 2 minus 2x squared times the derivative of the bottom, which would be 2 times 1 plus x squared to the 1 times 2x all over 1 plus x squared squared, which ultimately would be to the 4th then. Alright, and if we simplify that stuff, we can certainly do that. I'm going to show you an alternative way to do this in just a second here, but bottom line here is that you know, if worst came to worst, we can find the derivatives of this function, even though it's kind of a pain in the neck to do these polynomials and multiply all this out and stuff. We ultimately only need the value here at this point, so if we want to find the value here, we go 0 in here would give us 1, 0 in here would give us 0, 0 in here would give us 2, and this would be 0 also, wouldn't it? Yeah, so we actually would get 0 again, so that means that our f double prime would be 0 again. And again, we're looking for the first 4 non-zeros, so right now we've tried 3 of them, we got only 1 answer out of the deal, right? So we're going to need to find, we need to find 4 total. Okay. Alright, so let's think about this in an alternative way then, because obviously this is going to be way too time consuming for a 15-minute problem, right? Alright, so if we think of say a simpler one to deal with, and the one they suggested was to use 1 minus u and find the Taylor polynomial for it. If we put a 0 in here, we're going to get 1. Okay? And if we put a, if we do our derivative of this, remember our derivative of this, and this is an easy derivative to find because we can write it as 1 minus u to the negative 1, which gives us negative 1 minus u to the negative 2 times negative 1. Remember we got the derivative of the inside here to deal with. And so putting a 0 in here now, I would get 1 times negative 1 times negative 1, which would be 1. So that would simply be u, 1u, if you will. If I differentiate it again, I'd get 2. I'd get 1 minus u to the negative 3 times negative 1. So this time, at this point, I get 1 in here times negative 1 times 2, would be negative 2. So it'll be minus 2u squared over 2, factorial. Alright, and if we did the next one, it'd be negative 6, 1 minus u to the negative 4 times negative 1. So it'd be 6 ultimately, it'd be plus 6 u cubed over 3 factorial. And at this point, there's 4 terms here. Let's see how that translates. We may need to do more, but ultimately we get 1 plus u minus u squared plus u cubed. Alright, so again, the question is, how does that help us? Well, if we have something in terms of 1 over u, then couldn't we write 1 over 1 plus x squared now from that? Because ultimately, what did we do to, if this is our polynomial for this one, then this one we replace the u with the opposite of x squared, if you will. Because if we put a negative x squared in for u, we would get this. True? And so if we did that, we'd have 1, and then we'd have minus x squared, and then we'd have plus x to the 4th, and then we'd have minus x to the 6th. True? Alright. And then from there, to get from this to what we want, we got 2x is what we want. And again, we're just kind of trying to build the sequence from easier sequences. So if we did that, then it means we took this one and we multiplied it by 2x. So if we multiplied all these by 2x, we'd have 2x minus 2x cubed plus 2x cubed, that is, plus 2x to the 5th minus 2x to the 7th. The first one, yeah, it was plus, but we put, remember we're putting in a negative x squared. And in the original it was plus here, but we're putting in negative x squared to replace the u, if you will. Alright, and there's our first 4 non-zero terms. It does jive with the first term that we found by hand. If we would have continued that, we would have found all those terms eventually, but it would have been a real pain in the neck. We had to do a whole lot of algebra to get that done. Okay? So ultimately, again, we can build that from a simpler one, okay? One that we can find the derivatives for much easier, okay? By again just kind of breaking it down, going backwards now, looking back. Ultimately, if we had 1 plus u down here, that would be easier to deal with. If we just had a 1 on top, that would certainly be easier to deal with. Could we have done this from 1 over 1 plus u? Yeah, possibly. Alright, so that would be the first 4 terms, and the first 2 terms is worth a point. Second 2 terms are worth a point. And then the general term here, we need to recognize that the general term, we have an alternating situation. And then we have, we always have a 2 in here, so times 2. And then our x to the power here, we always have odd powers, so we have 1, 3, 5. We can always get an odd by going 2n plus 1. And remember, our first n is always going to be 0 here. So 0 power here is going to give us gone. 0 power here is going to give us 2x to the 1, which gives us 2x. If I put a 1 in here, that's going to make it negative. 1 in here makes it, oops, I that backwards. It should be, nope. I did have that right. Yeah, 1 in here is going to give us 2 plus 1, which is 3. And the 2 will give us 2 times 2, which is 4, plus 1 is 5, and so on. So general term, 1 more point. Alright. So, questions on that one? Alright, how about the next part here? It says, does the series that you found in part A, evaluated at x equals 1, converge to f of 1? And ultimately, explain why or why not. Okay. So, when we look at the series, okay, if we look at these, the series terms, okay, what's going on with these series terms? Yeah, we're multiplying by negative x squared to get from term to term here, and ultimately the values here are essentially getting bigger, aren't they? With our 2. Okay. All right, and if we check out our answer at 1, okay, does it converge to at 1? We know that we'd have a 2 in here. We'd have a 1 plus 1 down here, which would equal 1. And if we put in our 1 on the right hand side, we get 2 minus 2 plus 2 minus 2. So if we let f be 1, what would ultimately happen? Is that going to converge? I got 2 minus 2 plus 2 minus 2. It's just going to keep going back and forth between 2 and 0, isn't it? So therefore we'd say no, it's not going to converge. Alright. And on part C, it says that the derivative of the natural log of 1 over x squared is, in fact, this function we've been dealing with. And we want to write the first 4 non-zero terms of the Taylor series for ln of 1 plus x squared about 0. And so we know that if we have, we have the terms right here for the derivative. So what do we have to do to these terms to get back to the function they came from? We'll just anti-differentiate term by term. So if we do this first term, it's going to be x squared. This next term would be x cubed or x to the 4th over 4. And then x to the 6th over 6. And then x to the 8th over 8. And simplifying, we get x squared minus x squared over 2 plus x squared, x to the 6th over 3. Actually, x to the 4th, that is, sorry. And then minus x to the 8th over 4. Okay, we just had to write the first 4 only. So 2 points there. 2 points for the first 2, or 1 point for the first 2, and 1 point for the second 2. So 2 points total. Any questions on any part of that one? Okay. The last part then, part D. It says use that series that you found in part C, which remember is x squared minus 1/2 x to the 4th plus 1/3 x to the 6th minus 1/4 x to the 8th, and so on. Alright, so that's the series that represents our natural log of 1 plus x squared. And it says use that series to find a rational number a such that if we have this a number, we subtract the ln of 5/4 and take the absolute value that is less than 100. Okay, so we ultimately want to find an a value here so that if we do that subtraction, we would get a number that's less than 100. So the question is, can we find this said a value? Okay. All right. So ultimately, our ln of 5/4, okay, that's kind of a strategic number that they chose there. Because remember, this the function that this series represents here is ln of 1 plus x squared. And if we did 1 plus 1/2 squared, that would be the 5/4 in question, wouldn't it? Right here we'd have 1/2 squared, that's a quarter. Quarter plus 1 would be 1 1/4 or 5/4. Okay. So if we write it out as such, okay, and we use that 1/2 to make our estimate with our series, let's see what happens with that series. We get a half squared, we get minus a half times a half to the 4th. We get plus a third times a half to the 6th, and we get minus a quarter times a half to the 8th, and so on. Alright. So if we recognize that that strategic x value of 1/2 would give us that ln of 5/4, and then we can write an expression that gives us that series with that 1/2 as our x value, okay, which ultimately is exactly the same as ln of 5/4. Okay. Because again, this right here is the ln of 5/4 that comes from, or that can be reused to represent this right here. Okay. All right. So the issue then is if this right here is our series, okay, and we notice that what's going on with that series is that it's alternating. That's true. Would you agree? And if we were to write the terms out, this would be a quarter, and this would be a 16th times 2. That would be a 32nd. What's happening with the terms as we go from left to right here? Yeah, they're getting smaller. This is going to be 3 times 2 to the 6 is going to be 64. So it would be 192. Okay, we can see that these are clearly getting smaller. So what could be said about these terms? It's going to be a convergent series because the terms are getting smaller and it's alternating, right? All right. So bottom line here is that what we want to find, and again, remember, keep in mind that we're just trying to find some number a to make this sentence true. Okay. All right. And so if we let that that a value be our first 2 terms, so if we just approximate that a by the first 2 terms, think about if I took these first 2 terms, okay, and again these numbers are going to get smaller, okay, and so if I did the math on that, I'm going to get a quarter here, I'm going to get 32nd here, so this is going to be 8 32nds minus 1 32nd, be 7 32nds. Okay. So let's say we let that a come from the approximation just using 2 of our first 2 parts of our Taylor polynomial. Okay. So like I said, what is that going to show us? Well, let's see what happens if we try to plug it into that formula there. We got 7 32nds, okay, as our a value. And if we subtract our ln of 5/4, okay, and try to show that that's less than 1/100th, okay, ultimately, like I said, the answer to this, okay, and here's what I want you to remember, and I guess this is one of the things, and this is something that we have to try to remember, or else we're going to have a difficult time getting this right. Remember that if I were to pick the first 2 terms here, remember the next term after the first 2, and again, it doesn't have to be with 2. We could have done this with 3 terms and use the 4th term. We could have done this with 80 terms and use the 81st term, whatever the case may be. Okay, remember when we have the Taylor polynomial of however many terms we have, okay, that next term is an estimate for the error. Okay, and so this represents right here ultimately the difference between, okay, the function, the ln of 5/4 itself, okay, and the approximation. Okay, and ultimately this is the error, because remember this number right here is the approximation using 2 terms. True? This right here is the actual answer. Agreed? Okay. And so keep in mind, and this is kind of the trick part to it. We got to remember that this right here, okay, the error, this is the error. Okay, the error can always be represented by that next term. So when we take that down here, we do our next term, 1/3 times 1/2 to the 6th power. Okay, these 2 things are the same. Okay, and that's the tough part we got to recognize with this error-bound business, is that that if we were to make an approximation with 2 terms, right, which is what we did here with our 7 32nds, that's the approximation with 2 terms. Okay, that the subtraction of the approximation and the actual function, okay, that is, this right here is the error. Okay, and we also know that this is the error as well. Okay, that next term is the error as well. All right, and so with that said, if we recognize that, which again is not that easy to recognize, these are kind of tough problems, and they don't give us a whole lot of examples of it. But ultimately, if we do the math on this, we're going to get that 1 over 192 again. And what do we know about 1 over 192? It's less than 1 over 100. Okay. Now, my question to you would be then, just to illustrate again, because in the scheme of things, this is worth 3 points, and we don't really want to lose 3 points here. So if we have at least a pretty good general idea, hopefully we can get most of it. But bottom line here is why did we choose to use 2 terms to get this guessed A value here? Okay. Well, again, they just wanted us to find some A. Okay. So if we wanted to, could we have used the first 3 terms and got a different A value here? And had we done that, then we'd had something minus ln 5/4, and that would have equaled not the 3rd term, but it would have been the what? Would have been the 4th term. Okay. What would have happened if we just did the first term only? Okay, let's say, okay, well maybe it's the approximation after 1, maybe it's a quarter. If we did a quarter minus ln of 5/4, okay, that would be the error. And remember, the error at this point would be this one right here, wouldn't it? Okay, which would give us 1/32. And what would we have found in the equation then in that case if we would have chosen just the first one only? It doesn't work. So if the first one doesn't work, then you could try the second one. I mean, could you try the first one first and see if it works? Sure. It might be the first one would give us. And remember, the key issue here is that the more terms that we use here, okay, the less error there's going to be. Right? Okay. So that's one of the key things to remember, is that when we use a polynomial to approximate another function, okay, the more terms of the polynomial we use, the less error there's going to be. So since it worked for 2 terms, if we tried this with 3 terms, it would certainly work, wouldn't it? So again, that's the key thing to recognize here. And again, that's not, not the easiest thing to recognize, but like I said, the more we see it, the better. So we've seen quite a few at this point. We'll see some more as we go in the next couple weeks. Okay. All right, questions on that one?